Hello everyone and welcome to a new discussion which we are going to have on common derivatives of digital elevation models, and this is in two parts. So in first part we are going to have discussion on related with slope, and in second part in aspect, and we will also see some other details here. As you know that basically this is all for the understanding the terrain, and the best representation of terrain or the best data for terrain which we are having is a digital elevation model. But simple using digital elevation model will not give you those characteristics or derivatives. So we have to process that data, and the purpose here is to understand the topography. So now question is, what is basically topography? So basically topography, the surface characteristics such as slope, which we are going to discuss, aspect, relief and form of an area referred to as topography. So all these things which are part of topography, slope, and the most common derivatives of a digital elevation model are always slope and aspect. If you recall discussion related with TIN, and that is triangulated irregular network, we discussed that when TIN is generated, at the same time slope and aspect maps are also generated along with that. So that is in some way TIN is advantageous, but in case of a raster grid, which is a digital elevation model in our discussion, then these have to be derived separately. Now, as you know that the topography of a surface basically is represented through our digital elevation model, and as we are going for higher and higher spatial resolution digital elevation models, we can study the topography in more detailed form, and we can get even information which otherwise was impossible using survey topographic maps or survey topo sheets. And because there the terrain is only represented through contours, and visualizing seeing contour and visualizing topography was very difficult, and all these slope and aspect was not that easy. As you know that DM represents a topographic surface in terms of the elevation values measured at a finite number of points, and that geomorphic features or terrain features, terrain characteristics which are important from geomorphological analysis such as valleys, ridges, pits, etc. are very important derivatives of a digital elevation model. Now, if we talk about the geomorphological importance, then nowadays it is also possible, depending on the scale, if we choose appropriate scale for a terrain, then employing digital elevation model, we can also classify that terrain from geomorphological point of view as well. That means whether it's a peak, ridge, valleys, pits, etc. So this kind of analysis is also possible. In later discussions, we will bring that analysis also, that as one of the derivatives, that ultimately what we get the geomorphological importance. For like geomorphology is very important for civil engineers too, and there can be a completely separate course for importance of geomorphology for civil engineers especially. Because if somebody about to construct or finding a site, suitable site for a bridge construction on a river, and then they must understand the fluvial geomorphology, how that river is behaving in that part of the land. And therefore, if the same requirement is for a hilly terrain like Himalaya, then this valleys, ridges, and where the bends are there in the river, and not meanders. Meanders will be seen only in plain areas. So these bends of river, these are also important from sighting a very suitable location for a bridge. So, many times if this exercise has not been done, that means the geomorphology of the area has not been studied properly, then these projects might fail. So, whether it is a construction of a hydropower site or a reservoir or a bridge, any such thing, whether it is in hilly terrain or flat areas or plain areas, geomorphology should be studied first. And what is the best tool available today for us to understand the geomorphology is doing analysis, extensive analysis using digital elevation model. This I have been also telling that DM and satellite images are a storehouse of information. As much information as you can drive, these can provide you. The only thing which, the only requirement is that we have to understand first these two different data sets, though both are raster, but also we should know what are my requirements in a project or in a study or research, and accordingly I can exploit these two big data sets on a GIS platform, maybe in an integrated manner, to bring lot of insight of the terrain which is otherwise is impossible, not even sometimes through field investigations. So, this is very important. As also you know that DMs are commonly organized in in a grid format, and because of they are represented, or terrain is represented through a two-dimensional matrix, and therefore the computer manipulations or processing on computer becomes much easier. So, that is why these have become very popular data sets, and that is another reason, because lot of people are looking for digital elevation models. So, the organizations and countries are producing digital elevation models on regular basis, on higher and higher, for higher and higher spatial resolutions. So, this is very important. This is one more point which is a kind of repeat, which we have already discussed, that in a grid or in a raster, the cell size or pixel size is fixed and you cannot change. That means within a file, every cell will represent the same ground area, whereas in case of tin, it is adaptable to relief roughness. So, DMs or grid or satellite images do not allow that adaptation of relief roughness, but only tin model allows us to do that thing. Though by employing higher spatial resolution data or a small cell size data, that means representing a small ground area or field area, we can definitely go in much more detailed. But if we go for higher and higher spatial resolution, though our requirements may not be for that kind of resolution or scale, then it will be unnecessary, redundant, and it will require large storage space on your storage devices, and unnecessary, it may create some problem in future. Because remember, we have also discussed while discussing evaluating different digital elevation models and which one is the best. At that time we discussed that it is not always true that higher spatial resolution means more accurate representation of the terrain, may not be always true. So, one has to be also aware before we choose a much higher spatial resolution digital elevation model. Only one should go if it is required in our projects or in our studies. Tin we have already discussed. So, as you know that it is all triangulated irregular network in a one file or one tin. All triangles may be of different sizes and shapes, but they represent a triangular facets of the terrain, and that is the advantage because it is adaptable to relief roughness. And this information about the rough relief or relief roughness is only possible through this tin, and as you know that if input basically the sizes of triangles will depend on what is the density of my observations. If a density of observations is very high and each those observation points or data or spot heights are representing different elevation values, like in case of a hilly terrain, then these will adopt, or these will create smaller triangles, and a reverse in case of plain areas. So, what we do in order to drive these slope and aspects, the most common derivatives, and there are different variations are also there, or variants are also there. These we do it through a function which is called topographic function, and which calculate the for topography. Suppose if I am going to calculate for slope, then what it will do is a neighborhood function basically. So, it would look in the surrounding, and wherever against the center cell value, if value anywhere in the in the surrounding is less, then it will note that one, and that becomes the direction of the slope as well. So, and also depending on the variation, how much variation with the central cell in terms of values, that will also decide the slope angle, that means the value of the slope. So, the most common topographic functions or transformations which we work with digital elevation models, as I have said, one is the slope, which simply we can define is the rate of change of elevation. So, if two cells they are having a large elevation difference, then that means there the slope is very high. How much it is there, that can also be decided easily through these transformation functions. There is another term which is used, is called gradient. Now, this is basically the maximum slope is called gradient. So, you may have a sloping surface, but all parts may not have the maximum, So, for identifying that which part is having the maximum slope, that we call as gradient, which is also possible, and which we put also as one of the common derivatives of digital elevation model. And third common derivatives is the aspect, which is basically is the direction of a slope with reference to north. So, if I am having, for example, a sloping surface, so this will decide with the horizontal plane, this will decide what is the slope angle with this, but what is the orientation of this sloping surface with reference to the north will be decided in this analysis, which is aspect. So, this is the direction of a sloping surface with reference to the north is those who are geologists having geological or earth sciences background, they can understand much easier. Slope is something like dip amount, and aspect is the strike direction basically. So, slope is measured in the vertical plane, whereas aspect is measured in horizontal plane, because it is where you are bringing the direction, that means it has to be related with the north. Generally, we take north as a reference and do it as per our compass. Now, in order to calculate this slope or any these common derivatives which describe the topography at a specific location, what we resort, as earlier also mentioned, is the neighborhood. So, what is in the neighborhood, that relatively that will be decided. So, if neighborhood, suppose in a 3 by 3 matrix of cells, all cells are having the same value, that means the area is flat. But say in the southeast direction, in the corner, one cell is having lower value compared to the center cell, then we can say the slope is towards southeast direction. So, with reference to north, or that becomes our aspect. Now, what is the value of the slope in terms of either degree or percentage, that can be decided based on the difference between the central cell value and the, say in this example, southeast central and southeast cell value. So, in order to estimate these topographic functions or derivatives, generally a 3 by 3 window, a roving or moving window is used, and a as on the center cell, what we are deciding the value for the center cell on the point is usually used. So, if I am having a 3 by 3 window, then that window will move throughout all digital elevation file or 2-dimensional matrix, and whatever the value here for the center cell is decided by looking the neighborhood cells. So, this is how. Now, these cells of my this window 3 by 3 moving or roving window can also have their own weightages, and that can help us to find certain things in much easier way. It is very close to spatial filtering in terms of digital image processing. So, there are two kinds of filtering, one is based which is spatial filtering, another one based on the frequency, and that is fast Fourier transformation, other things. So, here we are going for spatial filtering which can be applied on any 2-dimensional matrix. Now, as we have been discussing that the most common derivatives of these topographic functions are slope and aspect calculation. Now, let us take first slope calculation. As you can see, it is based on simple trigonometry that rise upon run equal to tan theta, and this is what the tan theta is here. So, if this rise is much more compared to what the run, then you would have a larger tan value, or if it is smaller, then you may have smaller. So, relatively like here, this one is having very less value and degree of slope is being determined is 30. Here it is run and length is the same. So, tan theta or tan 45 here is like this 45 degree, and this tan theta here, and in this case when run is less and rise is very high, then we may have a much higher degree of slope. Now, the same slopes can also be represented in form of percentage. When we scale, instead of 0 to 60, if we rescale from 0 to 100, then we can also represent in terms of percentages. By default, in most of the GIS softwares, you would find that they will drive your slope in terms of degree, because we are much better, our brain is much better trained to understand the degree rather than percentage, but the option is definitely available in most of the GIS. It is a simple calculation that instead of having 0 to 60, you can 0 to 90, you can have percentage from 0 to 100 in that case. So, in that way it can be decided. Now, these values will be accordingly change. How these have been implemented in the software, one has to really check. The best one which I prefer always is keep in degree, which people understand very easily without any problem. Like here on the left image, as you can see that run is 100 meter, the rise is 20 meter. So, and when we substitute these values 20 and 100 in this equation, you get a 20% slope in that sense. Now, this is the one example of how the calculation is done, and using these roving windows or moving windows of 3 by 3 size. So, over the matrix a small window will move throughout and will try to see what is in the data, and accordingly it will calculate. So, if for example, here this is the input raster which you are seeing, and in order to understand, the values have been kept in a very simple range, that is between only 1 to 3, and this is the output raster basically, and that what is the value calculation here. The only problem comes when I have to calculate for the the boundary area. So, if my data is like here, that I am having a something like this raster, then one row, one column on left side, one row right side, one column top and bottom, for which the calculations cannot be done. Here the calculations cannot be done, because when I will keep my this moving 3 by 3 metric window, then because these areas I will not have any data available, and therefore a one one cell thick boundary would be there, though in this example that is not shown, but when you would do the real analysis, you can zoom it on the margins of your data set and you can definitely observe that point. Now here if I take for this central pixel like this 3, how the calculation has been done. So if you see here compared to the value 3, these are the things which are having in the surrounding are having lower value. So this is having what 36, but the other cells are having less values. But one may argue that why this value is higher, because this is part of an output. So in the surrounding of this one, that means mainly on the northern side, the values might be much lower, and therefore this cell is getting higher slope value. So for each cell that roving or moving window moves throughout your data set, throughout your matrix, and keep calculating slope value for the center cell, and this is how it is determined. So the use of another very important part is, which I was very keen to discuss here, and it is very important, is called jet factor. Now as you know that digital elevation model, when I was discussing introduced digital elevation model, and at that time I said that there are two resolutions associated with any digital elevation model. One is for horizontal and one is for vertical, because generally the data set might be represented for horizontal, it might be represented through degree decimals, but the height or the cell which are representing the height above mean sea level will be having value in meters. So that means the XY scale or horizontal scale is completely different than vertical scale. So when we go for this slope aspect or many other such analysis, we find that there will be always a question about jet factor. What should be the jet factor? Jet factor basically will allow you to rescale one of the scales, and either you rescale the horizontal scale or vertical scale. So the use of jet factor is essential for correct slope calculations, not only slope but many other calculations, when the surface Z units are expressed in unit from the ground of XY unit. That means the horizontal scale is not equal to vertical scale in case of a digital elevation model. Only if it possible when I am having UTM projection easting, northing, and everything is represented in meters for horizontal also. So my vertical scale, that is Z values and XY values, all are in meters, then I can choose jet factor as one in my software. Otherwise I have to provide a value. So the basically this is we have to control and take care about this. Now when we bring this data set or our digital elevation model which is required for calculation of a slope, then the range of values in the output will depend on the type of measurement units. That means that the roving matrix, whether it is also having some weightage or not, or every cell is having value 1. So the biasness or weight can also be assigned to that. So for degree, the range of the slope values will depend, of course, 0 to 90 degree, or in case of percentage 0 to 45, 0 to 100 in case of percentage, and sometimes we may get value 0. Like here in this example, this value, this cell is bearing value 0 and the 0 has been, or it's a no data basically. Or if it is flat terrain, then value would be 0 and no, of course it is really flat, so no slope at all, 0° slope. So this center cell for this 3 by 3 matrix will go through the entire data set. If it finds no data, it will result in no data. But if it finds a flat terrain, that means all cells below that 3 by 3 matrix are having same value, then the center cell will be assigned 0 value, not no data. So, no data will always result no data, like in this example, this is no data, result will all no data, whereas the all surround 3 by 3 cells, all 9 cells, if they are having value, same value, then 0 will be assigned. That means it is declaring is a flat terrain in compared to the neighborhood. Now, there will be a question, why only 3 by 3 roving moving window? This moving matrix, why not 5 by 5, why not 7 by 7? Yes, it can be done, but it will bring more computation time and may not bring very good results either, because it will smoothen the things which you do not want. So, this is the best option available, and most of these softwares have implemented only for 3 by 3, but I am sure that some software might allow you to design your own matrix and changing the dimension. Instead of 3 by 3, you can go any odd number. So, neighborhood cells will decide what should be the value. Here it is let us take another example, but now I am introducing two different types of slopes. One is the planar slope, and in case of planar slope, this rate of change or delta of the surface is in horizontal, that is dx, dz and oblique dx, and the vertical dz by dy. Directions from the center cell determine the slope, and the basic the function or algorithm is used to calculate the slope is something like this, that the slope in degrees is a10, and this is is square, then this square overall under root multiply by this truncated version, which is 180y divided by pi. So, this value has to be multiplied with that, and then you get slope in degree. Now, this slope algorithm or this concept can also be interpreted as follows, that the slope degree a10, that is rise upon run, multiply by this 180 by pi, or this 57.29578, and where you know that rise run is this function. So, by this you get the planar slope calculation. Further, if we see that the rate of change in x direction for the center cell, that is the E, is calculated like this, and then rate of change in the y direction is calculated like this. So, for each direction, because say horizontal and there are two directions x and y, therefore, such calculations will required, and then finally you get a slope. So, in this example, like here this is my roving or moving window, which is on run on this one, this is my input raster, and when this is what the result I get, that these are slope output which I am getting in terms of degree. So, likewise I can do this calculation. What are the important things to remember is of course Z factor, and this because if Z units are not same as or rather vertical units are not same as horizontal units, one must take care about Z factor. When we go for percentage slopes, basically we are multiplying with 100, and if rise is a different unit than run, then we should take care about Z factor, otherwise it will bring completely wrong results. And so, while doing this demonstration on computer of slope calculation, I will show you that what the difference it will bring if you do not take care about the Z factor. So, that means the elevation and horizontal units must be same type in meters, and if they are not, then jet factors so cannot be 1. Generally by default most of the softwares would keep jet factor as 1, assuming that horizontal and vertical scale are same. But if they don't know whether my data is in the digital elevation model, horizontal is in degree decimal, whereas my units for vertical are in meters. So this change is required. For average jet factor for India, which we have calculated, is 0.5 times 0.89. So how this figure has come? Basically, you are converting through this jet factor your meters into dt. So when both are, then the correct calculations of slope would be there, or correct estimation. So jet factor is only applicable in case of planar method. This is one example, typical example. This is the input your digital elevation model when it is subjected to for the slope calculation, and this is what output you get in degree. Now how you classify this one is a different thing. I may classify only in 5 categories and have range. So the classification methods of continuous data we have already discussed, so that you can apply. Instead, because by default it is always equal distance classification will be done, that each class will represent almost the equal variations in the slope. But if I want to change to equal area or quantile or standard deviation, I can choose accordingly. This is there are now different variations which can be done, or which can calculations can be done on a GIS platform using some other methods rather than what the standard method. So there is one horn method, and that slopes can also be calculated in percentage, like here it is in degree. Now what in horn method is that this is my these are my these 3 by 3 cells, and they have been given here in this example Z1, Z2, Z3 like this. So given 3 by 3 cell neighborhood with the elevation Z1 to Z9, Z1 to Z9, with the cells separated by distance L. Now here, because in both directions it has to be calculated, so dz over dx, that is a north south gradient, will be calculated. When I do dz by dy, then east west gradient is calculated. So in horn method, this is what it is followed. He gave this idea in 1981, and this is how the calculation will be done. Once these values are substituted, you get the example also. Now 4 cell instead of 3 cell method, 4 cell method was also given, and that is basically Jevonberger and Thorne method in 1987. So you may find lot of variations, because once somebody has developed initially a 3 by 3 matrix to calculate the slope, people will definitely think why 3 by 3, why not 4 by, why not 5 by. So that may bring new developments in this, but the basic concept will remain same. These variants will bring little different results, not major differences. And that is always true, that after each and every calculation one must go and check for errors. So you have to have some idea about the terrain before you calculate for slopes. If you are already having idea of the terrain and a value is coming accordingly, you may get satisfaction, or you may say it is now calculating correctly. So one has to be really careful about the jet factor and other things. Now these the nearest point weighted more than the diagonal neighbors, if I choose this horn method. This also known as the Sobel operator in terms of your spatial filtering in digital image processing. There we call as a Sobel filter. Here it is Sobel operator, which can be used for edge detection. So, there in digital image processing of remote sensing data, we use this spatial filter, which is a Sobel filter, for edge detection. So, wherever we are having the sharp changes in the cell values, those are highlighted through this filtering technique. Because in this horn, the center cell actually has no influence on the calculated slope, maybe a disadvantage. So, depending basically, depending what you are going to calculate here. So, this is how in one direction it is in the east-west gradient direction. Now, default slope calculation method in ArcGIS is Horn's method. This has been implemented, not the other one Jaberger or Thorn method, but Horn method that has been implemented in default. But if you want to calculate by employing other methods, those options you can also explore. And for example, there is another one which was given by Fleming and Hofer in 1979, which is the next best method or algorithm after this Horn method, is that it takes ZX, ZX and sorry, DZ and DX and DZ and DY using cardinal direction. Now, these cardinal direction I will just discuss in a minute, and the center cell not taken into account for the calculation, completely ignored. Now, about the cardinal direction. So, these directions with reference to north, like north, south and northeast, southwest, and when these are there, basically the north, south, east, west, we say cardinal direction. When northeast, northwest, south, west and southeast are there, then we say ordinal direction. In case of aspect, all cardinal and ordinal directions are used. But in case of our slope calculations, only cardinal directions are in this particular method are used. So, that it takes that using cardinal directions only east west or north south. This is what you have been seeing. No diagonal calculations are possible at that stage, but later on that is also considered. Now, diagonal returns or diagonal methods are also there, which is the basically modifications of Fleming and Hofer methods, which takes dz over dx and dz over dy using ordinal direction, and therefore, that is why the name is diagonal. And the center cell not taken again into account for calculation like here, and this is how the result will come about when you employ this diagonal return. Various variants are available. The simple method is basically by the concept as which uses the difference in elevation with its neighbor to calculate the slope. So, whichever the cell against the center cell is having low value, that becomes basically the slope, the amount, the difference will decide the amount, or in terms of degree we can calculate, and in the it will also decide the direction both in cardinal and ordinal direction. So, 8 directions would be possible. Only that is basically decided for aspect. So, only method where center cell is actually taken into account is through this simple method. Ranks which are relatively low for slope calculations, because it depends on how people prefer, but this is what is the most popular one, though it may rank among calculations from very accuracy point of view may be low. And this is how again this kernel, also these roving or moving windows are also called kernel. So, you can do the calculation like this. Now, I have already shown the same digital elevation model was subjected to Horn method. Now, this is the Jaberbergen and Thorne method. I will also show you the comparison when the same digital elevation model was subjected to two completely different methods. This is how you get the results also. So, for one particular cell against cell, so they 1, 2, 3, 4, 5 against 5 individual cells when the comparison was made. Here we are getting 1.2 degree, here we are getting 3.3 degree. So it is more than double. Again here 8.6 degree, it is giving 5 degree. So as you go towards higher degree, you may get a different thing. Now here it is almost same, 29 degree it is giving the lower value, 49 degree it is quite close to that one. So that means spatially it is varying when we compare two slope based on two different methods, Horn and Java-Vernon and Thorne method. Now which one is correct? Again it has to be decided the same way as we decide which interpolation method is correct. You select certain points, if it is possible, go in the field, check it and then choose the appropriate one. So by this way you can get, otherwise the simple method or Horn method which has been implemented is quite good, except in certain cases you may get a lot of variations between two methods, but visually of course you may not realize that they are having different values. But when you go and probe these derivative or these products, slope products which have been generated using different methods on individual cell basis, this is what the result you get, that the slope values may vary very largely, especially at the lower end of the slope. So with this I end this discussion. Thank you very much.